Let me welcome you to this lecture. We have been discussing different application of group theory in chemistry, and we have so far looked at how one can use group theory for solving problems in vibrational spectroscopy, as well as how one can find out a different combination of atomic orbitals or orbitals to form to get this symmetry adapted linear combination. Now we will discuss how one can use group theory in bonding, and one important question that we raised in the beginning of this course is so for example, if we know that in case of a tetrahedral molecule the central atom has sp3 hybridizations. For example, in case of methane that is the case, but how do we know that the hybridization that is a sp3 hybridization gives us a tetrahedral molecule? We can work this out by using group theory. So let us take a tetrahedral molecules, methane as the example here, and let us find out the symmetry of the sigma bonds for a tetrahedral molecule. So now we know we can take these bonds in tetrahedral molecule as the basis, and we can write a reducible representation by taking the bonds as the basis. Here these are the sigma bonds, and if we take now the tetrahedral, the TD character table, and we find out the characters of different symmetry operations for this reducible representation. The symmetry operations in case of a tetrahedral molecule with TD point group is, we have already found out. So there are 24 symmetry operations, and these 24 symmetry operations are in 5 different classes in case of a tetrahedral molecule. So let us find, that is gamma sigma bond, by taking the bonds as the basis. Now let's also write maybe R1, R2, R3, R4 to denote these bond factors. Now we know that if when we do the identity operation, none of the bonds change position or direction. So the character for identity operation is going to be equal to 4. And when we do C3 operation, we know the C3 axis passes through one of the CH bonds here, and then when we do C3 operation, only one CH bond will remain static and it will not change direction, that particular CH bond. So if we take the C3 axis passing through this hydrogen and this carbon atom, then R1 bond vector is not going to change direction as well as position, while R2, R3 and R4 are going to change position. So these bond vectors are going to contribute 0, while R1 is going to contribute +1. So total character for C3 operation we will have is equal to 1. Now when we do C2 operation, now the C2 axis in the tetrahedron does not pass through any of these CH bonds here. So because the C2 axis will bisect the angle between the HCH bond angles essentially, and that is how we have it is not 6 C2, it is 3 C2 axis we have in case of tetrahedron, because when we take the tetrahedron, or when we place the tetrahedron inside a cube, we know that we have the atoms, the hydrogen atoms will lie on alternate corners of the cube, and the C2 axis passes through opposite faces of the cube, and that is how we have 3 C2 axis in case of a tetrahedron. So none of the CH bonds passes through the C2 axis, and that is why when we do C2 operation, all the bonds are going to change position, and that is why the character of C2 operation is going to be equal to 0. Same is the case in case of S4 operation, because we know when we do S4 operation, the S4 axis are essentially collinear to the C2 axis of symmetry, and that is why all the bond vectors are going to change position when we do S4 symmetry operation, and the character we will get is going to be equal to 0. Now for sigma d, each of these sigma d contains 2 of these CH bonds, and that is why when we take this sigma d that is on the plane of the board, it will contain the R1 and R2 bond vectors, and it will bisect the angle between these R3 and R4 bond vectors, and that is why R3 and R4 are going to change position, while R1 and R2 are going to remain static, and their orientation does not change as well as their position does not change, and that is why R1 and R2 are going to contribute +1 and +1, while R3 and R4 are going to contribute 0 and 0. So total character here is going to be equal to +2. Now we have the reducible representation for by taking the sigma bonds as the basis for a sigma bonds of a tetrahedral molecule as the basis. Now if we take the TD character table and then find out the irreducible components of this reducible representation gamma bond, what we will find is that gamma sigma bond is equal to A1 plus T2. So it is composed of two irreducible representation, one A1 irreducible representation and other one is a three-dimensional irreducible representation, that is the T2 irreducible representation, and you can work this out by taking this reducible representation and find out how many times each of the irreducible representation in TD point group appear in this reducible representation, and this is the result you should get. So this tells us that the sigma bonds here are essentially formed by combination of or formation of a hybrid orbital, and these formation of hybrid orbital, and these hybrid orbitals are essentially formed by one atomic orbital of A1 symmetry and another a set of 3 atomic orbitals of T2 symmetry. Now we should go back and look at the TD character table and then see which atomic orbitals essentially transforms as A1 irreducible representation, and again which atomic orbitals transform as T2 irreducible representation. If you look at the TD character table, what you will find that the s orbital transforms as A1 irreducible representation in the TD character table, and for the T2 irreducible representation, you will find there are two sets of atomic orbitals essentially transformed as T2 irreducible representation, that is Px, Py, and Pz, as well as dxy, dyz, and dxz atomic orbitals. Also, because if you see against the T2 irreducible representation, you will see x, y, and z coordinates transform as T2, as well as dxy, dyz, and dxz together they transform as T2 irreducible representation in TD character table. So that means these atomic orbitals, or this set of atomic orbitals, transform as T2 irreducible representation in TD character table, and from here we can see that we can have two different combinations of atomic orbitals to form a tetrahedral molecule. The one combination is where we combine one s orbital with 3 p orbitals, so that is sp3 hybridization, gives us a tetrahedral molecule, and we have seen this, or we have learned it earlier that when in case of a tetrahedral molecule, the hybridization of the central atom is sp3. Similarly, we can also combine one s orbital and 3 d orbitals, that is the xy, the yz, and the xz, and then we have sd3 hybridization, and the sd3 hybridization will also give us a tetrahedral geometry. So, but while in case of methane or most other molecules, we assume that it is sp3 hybridization because the energy of these s and p orbitals are compatible with each other. So that is why hybridization can occur, but the energy of s orbital with is not compatible with the energy of d orbitals, and that is why sd3 hybridization cannot occur. But from symmetry point of view, we know now that we can have both sp3 as well as sd3 hybridization, and both of these hybridization will give us a tetrahedral geometry. So you can do this exercise for molecules of antisymmetry. Say for example, you can take a square planar molecule, you can take a octahedral molecule, and you can as well as take a trigonal bipyramidal molecule, and then find out, we can take the sigma bonds of these molecules as the basis, find out the reducible representation, and once you find out the irreducible components of this reducible representation, you will know exactly what hybridization or what combination of, or combination of which atomic orbitals can give those geometries. So we have seen that the application of group theory makes this question, answering this question, very easy task for us. So we will now see some more application of group theory in bonding. That is, we will try to answer how we can draw molecular orbital diagrams for polyatomic molecules. So we will take as an example of a polyatomic molecule, we will take an octahedral complex as the example here, and let us try to draw the molecular orbital diagram of an octahedral molecule. Now here we assume also that all the bonds here, all the metal ligand bonds here are sigma bonds. So this is the molecule, octahedral molecule that we have taken over here. And now if we take the sigma bonds of this octahedral molecule as the basis, we will write the gamma sigma bond here also, as well as we have done in case of the, so OH is the point group, is the OH point group, and we will write all the symmetry operation or the classes, different classes in OH point group here, and then find out gamma sigma bond here. So we know there is identity operation in OH point group. Then we have 3 C4 axis of symmetry, and this C4 axis of symmetry essentially produces, each of these C4 produces 2 symmetry operations, and that is why we have total 6 C4 operations, and all of them are in the same class. Then we also have 4 C3 axis of symmetry, and these 4 C3 axis of symmetry are all are in the same class, and each of these C3 produces 2 symmetry operations, and that is why in this class we have total 8 symmetry operation. Then we have 3 C2 axes which are collinear to the C4, and which are essentially coming from C4 2, and then we have, apart from that, we have another set of C2 axis of symmetry, these 3 C2 axis of symmetry. Then we have also the S6 axis of symmetry, and these S6 axis of symmetry, we have total 4 S6 axis of symmetry, and each of these S6 axis of symmetry produces 2 symmetry operations, and that is why we have total 8 S6 operation. Apart from that, we also have 3 S4 axis of symmetry, and these S4 axis of symmetry produces 2 distinct symmetry operations, and that is why 6 S4 symmetry operation. Then we have the inversion operation here, and apart from that we have 3 sigma H, and then we also have 3 sigma D symmetry operations. So we have we'll have to rewrite these here because of lack of space over here. So we'll write here HC3. These are 3C2 collinear to C4. Then 3C2, which essentially bisect the sigma H planes here. Then we have 8S6, we have 6S4, we have I, we have 3 sigma H and 3 sigma B. So total we have 7, 15, 15 plus 3, 18, 18 plus 3, 21, 21 plus 8, 29. Then we have 35 including these. So 36 here, 36 plus 6, we have 42 symmetry operations. And apart from that, we also have, we have 6 sigma D. So that makes 6S4, 3 sigma I. So we have a 7 plus 15 here, 15 plus 3, 18, 18 plus 3, 21, 21 plus 8, 29, 29 plus 6, 35, 36, 36 plus 3, 39, 39 plus 6, 45 here. So we are missing few symmetry operations here. So E, 6C4, 8C3, 6C2. So there are 6C2s. These are, there we have total 6C2 here. Now 3C2 symmetry operation. Because these C2 operations bisect the sigma H planes, we have total 3 sigma H planes, and that is why total we have 6 such C2 axes which bisects the sigma H planes. So we have discussed about this earlier, and these are the 48 symmetry operations in an octahedral molecule. So now let us find out the characters of this reducible representation gamma sigma bond here. So total we have 6 sigma bonds in this molecule. So the character of identity operation is going to be equal to 6. Then we have a C4. When we do C4, we know that it passes through 2 of these ML bonds here. So all the rest ML, so 4 ML bonds are going to change position, and only those ML bonds through which the C4 axis passes through are going to remain static, and they do not change position as well as direction. So that is why here we have class 2. And then when we do C3 symmetry operation, the C3 passes through the center of the opposite triangular faces. So that is why all the ML bonds are going to change position when we do C3 operation, and the character is going to be equal to 0. These C2 are collinear to the C4 axis of symmetry, and that is why when we do this C2 again, 2 of the ML bonds are going to remain static, and the rest 4 are going to change position, and that is why the character is going to be equal to 2. These 6 C2 axis passes through the, this is how they pass through. So that is why when we do this C2 operation, then all the ML bonds change position, and that is why the character is going to be equal to 0. Again, when we do S6, S6 are collinear to the C3, again the character is going to be equal to 0. When we do S4 operation, S4s are collinear to the C4 and as well as the C2 axis of symmetry, but when we do the S4, we also do C4 and then we do sigma. When we do the sigma H, so when we do the C4s, these 2 ML bonds are going to remain static and they do not change direction. But when we do the sigma perpendicular to the C4, then these bonds are going to get swept and they change position, and that is why again when you do S4, the character is going to be equal to 0. When you do inversion, all bonds change position we again get 0. When we do sigma h, 4 of these ML bonds do not change position, and that is why the character here is equal to +4. And when we do sigma d, again this sigma d, when we do it, say it contains only 2 of the ML bonds, so that is why the character is going to be equal to +2. So this is the reducible representation that we obtain by taking the sigma bonds of an octahedral molecule as the basis. Now, when you find out the irreducible components of these reducible representation gamma sigma bond of an octahedral molecule, that is the irreducible components of this reducible representation, by using the OH character table, you will find that this is going to be equal to A1G plus EG plus T1U. So what it tells us that when the ligands approach the metal center to form an octahedral complex, the ligand orbitals have to combine together first in such a way that they form molecular orbitals or ligand group orbitals of D symmetry, that is E1G, EG, and T1U. So with this knowledge, let us try to draw the molecular orbital diagram of an octahedral complex. So let us first draw the symmetry of the metal orbitals. We know, so this is the metal, and let's also draw the energy axis. This is the energy axis we know, and this side we will draw something known as ligand group orbitals. That is, ligand orbitals combined together to form orbitals of the right symmetry, which can come and form an octahedral complex. So we call them ligand group orbitals. Now, metal orbital, there are metal 3D orbitals, S4s orbital, and 4p orbitals. So if you look at the symmetry of the d orbitals in case of an octahedral complex, you will find that the metal orbitals have the 5d orbitals have Eg and T2g symmetry. So we can write Eg plus T2g. That is, the x square minus y square and dz square orbital have Eg symmetry, and the xy, the yz, and the xz orbitals together they transform as the T2g irreducible representation. Then s orbital has A1G symmetry, and the 4p orbital have T1U symmetry. Now we know that the ligand group orbitals, or that for formation of an octahedral complex, that is ML6, has the ligand group orbital symmetry of the ligand group orbitals we have already deduced. That is, the symmetry of the 6 ligand group orbitals which can form an octahedral complex is A1G plus EG plus T1U. Now we will draw the energy of the ligand group orbitals at a lower energy level than the energy of the metal 3D orbitals here, because we know we are drawing the molecular orbital diagram for a sigma, for a complex where only sigma bond is present, or only for sigma donor ligands. These are ligands like, say, for example, ammonia, where in case of ammonia, we know the orbital or the electrons which are going to be donated to the metal are in an sp3 hybridized orbital, which are formed by essentially 2s and 2p orbitals, and these orbitals have much lower energy than the energy of the 3d orbitals or the 4s and 4p orbitals of the metal. That is why we draw the energy of these ligand group orbitals at lower energy than the metal energy of the metal orbitals. Now we will draw the molecular orbital diagram, that is by combining the orbitals of the same symmetry together to form molecular orbitals. So we will take a metal orbital and a ligand group orbital of the right symmetry and combine them together to obtain the molecular orbital diagram. So let's let's first take the A1G bonding here from the ligand group orbital, and we see that metal orbital there is a metal orbital of A1G symmetry, so we can draw it in this way. So A1G bonding and A1G anti-bonding, so A1G star we can write. Then we have T1U as well as T1U here, so we have T1U bonding and T1U anti-bonding, T1U anti-bonding in this way. Then we have EG and EG of LGO and EG of metal. So we have EG, EG star. So that is how we can draw. Then we see that the metal orbitals, there are metal orbitals which have T2G symmetry, but no ligand group orbital have T2G symmetry. So these orbitals are essentially the T2G set of orbitals will not participate in sigma bonding and they instead remain non-bonding in nature. So let's also draw here the degeneracy of the, let's maintain the degeneracy of the orbitals here. As we know that because T1 is triply degenerate, here EG is doubly degenerate, it's a two-dimensional irreducible representation. So that is how we can maintain the degeneracy. So now let us try to fill the electrons in this molecular orbital diagram. So we know the ligand, these are sigma donor ligands, and there are 6 ligands surrounding the metal center, and these 6 ligands donate total 12 electrons. So 12 electrons come from the ligands. So and also we see that let us try to fill these by electrons over here. So 2 electrons will be this T1G molecular orbital bonding. Then this T1U is triply degenerate, so total 6 electrons can go over here. So 2 plus 6 total 8 over here, and then 4 electrons in this EG bonding molecular orbital. So we have now filled so far 12 electrons over here, and these electrons essentially come from the ligand. These are ligand electrons because what we see is that the energy of these molecular orbitals are closer to the energy of these ligand group orbitals, while the energy of these two molecular orbitals are essentially closer to the energy of these metal orbitals. So now all the electrons that are present in the metal are going to be filled over here in these molecular orbitals, that is the T2G molecular orbitals and EG star molecular orbitals. So this is what we have already learned from our coordination chemistry theory, that the difference in energy between the T2G molecular orbital and T2G set of d orbitals and the EG set of d orbitals is essentially known as the crystal field stabilization energy. And here we can show that this is the crystal field stabilization energy. But here what is to be noted is that the T2G set of molecular orbitals or T2G set of orbitals, d orbitals in metal, they are non-bonding in nature, they do not participate in sigma bonding, while the EG set of d orbitals in the metal, they are anti-bonding in nature, and if we start filling electrons in the EG set of orbitals in the metal, then the molecule is going to be essentially unstable in nature. It's because this is an anti-bonding molecular orbital. So this molecular orbital diagram we should learn carefully, and this also allows us to understand many other principles of chemistry like the 18 electron rule and such electron counting rules. This only by drawing the molecular orbital only by drawing the understanding the molecular orbital of these molecules, we will be able to tell how these rules have been drawn, or how these rules have evolved. So this is the molecular orbital diagram of an octahedral complex with only sigma bonds. In the next lecture, we are going to learn how one can draw, or how one can use group theory to draw a molecular orbital diagram where pi bonding, in a complex where the pi bonding is also present. So with this, let me conclude this lecture. So what we have learned during this lecture is that how one can use group theory first to draw, first to find out the combination of atomic orbitals which form hybrid orbitals, orbitals in molecules of different geometry. So we have taken the tetrahedral molecule as an example, and we have seen that two combination of atomic orbitals, that is one s orbital and three p orbitals, sp3 hybridization can give tetrahedral geometry. Apart from that, we have seen that if we take one s orbital and as well as three d orbitals, that is the xy, the xz, and the yz orbitals, and combine these together to form sd3 hybrid orbital, that is also going to give us a tetrahedral geometry. Then we have seen how we can use the group theory principles to draw molecular orbital diagram for complex molecules, and we have taken the octahedral molecule as the example, and we have drawn the molecular orbital diagram for this octahedral molecule. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.